3.5 Integrating using partial fractions. Now, in the regular A-level maths course, you used partial fractions to integrate some rational functions, and that's what we'll be doing in this video. So let's take a look at an example to illustrate what we're talking about. Example number 13, we have to prove that the integral of 1 over a squared minus x squared with respect to x is equal to 1 over 2a times the natural log of a plus x over a minus x plus c, where a is a real constant. Now, to do this, we need to use the idea of partial fractions to help us do this. We begin with the 1 over a squared minus x squared, and if we rewrite this, we can rewrite this as 1 over a plus x lots of a minus x. And if we use partial fractions, we have a over a plus x plus b over a minus x. Now, if we multiply both sides by a plus x lots of a minus x, you can see over here we end up with 1, which is equivalent to a lots of a minus x plus b lots of a plus x. And this is what we'll be working with. Now, we need to choose values of x such that brackets disappear. For example, when x is equal to minus a, the b bracket disappears. We're left with over here 1, which is equal to a lots of 2a. So therefore a is equal to 1 over 2a. And when x is equal to a, we have 1 which is equal to, well, this a bracket disappears. We're left with b lots of 2a. So therefore b is equal to 1 over 2a. And therefore, knowing the values of a and b, we can therefore conclude that 1 over a squared minus x squared, that's equivalent to 1 over 2a lots of 1 over a plus x plus 1 over 2a lots of 1 over a minus x. So we can use this idea to help us integrate this result. So therefore, the integral of 1 over a squared minus x squared with respect to x, this is equal to, well, if we consider this bit and take out the 2a as a common, 1 over 2a as a common factor, we have 1 over 2a lots of the integral of 1 over a plus x with respect to x plus 1 over 2a lots of the integral of 1 over a minus x with respect to x. So if we integrate, you can see here we've got 1 over 2a times by the natural log of the mod of a plus x minus 1 over 2a times by the natural log of the mod of a minus x. And we add on this plus c. So here we've got 1 over 2a times by the natural log of, if we combine the logarithms, a plus x over a minus x plus c, which is exactly what we wanted to show. Now, if the denominator of a partial fraction includes a quadratic factor of the form x squared plus c, where c is greater than 0, you cannot write it as a product of linear factors with real coefficients. However, you can still write it in partial fractions, where the partial fractions corresponding to the quadratic factor has a linear numerator and a quadratic denominator. Let's take a look at an example to help illustrate this. Let's suppose we've got something like 20 over x plus 3 lots of x squared plus 1. Now, we can split this up using partial fractions. We've got two terms. The denominator of one of them will be x plus 3. The denominator of the other one will be x squared plus 1. Now here, because on the bottom we've got a linear denominator, the top will be numerator 1 degree less than the linear term, so here we'll just have a constant term, we'll call this a. As we see over here, we've got a quadratic, and if the quadratic over here, the denominator, if we have a quadratic on the denominator, the numerator will be linear. So on the numerator we'll have something of the form bx plus c. And this is similar to algebraic division, depending on how you've been taught it. And now, for us to find the values of a, b and c, we need to multiply both sides by x plus 3 lots of x squared plus 1. So on the left hand side we've got 20, on the right hand side we've got a lots of x squared plus 1 plus bx plus c lots of x plus 3. Now the question is over here, how do we find the values of a, b and c? Well, if I set x equal to minus 3, this bracket will become 0, so this entire thing will become 0 because we're multiplying by 0, and that will allow us to find a. But the question is, which value of a do we choose, which value of x over here do we choose such that this bracket becomes 0, and then from there we can find out what b and c are. We don't want to think about complex numbers because that makes things too complicated. So instead what we'll do is compare coefficients. Now before we do anything, let's actually set x equal to minus 3. If we do that, we've got 20 equals a lots of, well here we've got minus 3 all squared, which is 9, plus the extra 1, that's 10. And then here we've got 0 multiplied by another bracket, so this entire thing will become 0. So therefore a is equal to 2. Now if we compare coefficients, we can then find the value of b and then find the value of c. So if we compare the x squared terms, you can see on the left hand side we've got 0 of them, but on the right hand side we've got a times by x squared, and then we've got bx times by x. So we've got a plus b equals 0. And knowing that a is equal to 2, we've got 0 equals 2 plus b, b is equal to minus 2. And if we compare the x terms, on the left hand side we can see we've got 0 of them. You can see here there's no x term for this bracket, but if we take a look at what we have over here, you can see we've got bx times by 3, so we've got 3b, and then we've got c times by x, so we add on plus c. So we've got 0 equals minus 6 plus c, so c is equal to 6. And knowing the values of a, b and c, we can rewrite this entire result. So therefore what we can conclude is 20 over x plus 3 lots of x squared plus 1. This is equivalent to a over x plus 3, so here we've got 2 over x plus 3 plus bx plus c, so here we've got 6 minus 2x over x squared plus 1. And the idea is over here, if we were to integrate something like this, we'd split it up into partial fractions first, like we've done over here, and then integrate the terms separately. Example number 14, we have to show that the integral of 1 plus x over x cubed plus 9x with respect to x is equal to a times by the natural log of x squared over x squared plus 9 plus b lots of the arctangent of x over 3 plus c, where a and b are constants to be found. So the first thing we need to do is write all of this in an integrable form. So if we consider the 1 plus x over x cubed plus 9x, on the bottom we can factorize out an x, so we've got x lots of x squared plus 9 on the bottom, and on the top we've still got the 1 plus x. Now we can use the idea of partial fractions to help tidy this up even further. This will be equivalent to a over x plus bx plus c over x squared plus 9. Of course, a quadratic denominator means we've got a linear numerator when we split up using partial fractions. So if we multiply through by x lots of x squared plus 9, we've got 1 plus x, which is equivalent to a lots of x squared plus 9 plus bx plus c lots of x. And now if we expand out, we have a x squared plus 9a plus bx squared plus cx, and if we collect like terms together, we have a plus b lots of x squared plus cx plus 9a. And now if we compare coefficients, what you can hopefully see over here, if we compare the x squareds, on the left hand side we've got 0, and on the right hand side we've got a plus b of them. If we compare the x's, on the left hand side we've got 1, on the right hand side we've got c is equal to 1. And now if we compare the numbers, on the left hand side we've got 1, on the right hand side we've got 9a, a is equal to 1 over 9. And now from this first equation, a plus b equals 0, you can see that b is equal to minus a, so therefore b is equal to minus 1 over 9. And now if we tidy all of this up, hopefully here you can see we've got 1 plus x over x cubed plus 9x being equivalent to a over x, so here we've got 1 over 9x plus bx, so we add on, minus 1 over 9x plus c, which is 1, and then we divide this by x squared plus 9, and we need to write all of this in an integrable form. Now to do that, we still have this 1 over 9x, that's not going anywhere. This, as we saw in previous examples, we can split up even further. We can split this up as minus 1 over 9 x over x squared plus 9 plus 1 over x squared plus 9. So if we tidy all of this up, well, eventually we're going to have to integrate everything. So if we write these two in the form f dash over f, here we've got 1 over 9, lots of 1 over x, and here, well, on the top we want a 2x, on the bottom we still have this x squared plus 9. This ensures this is of the form f dash over f, but to maintain what we have over here, hopefully you can see we need a 1 over 18, because 1 over 18 times by 2 gives 1 over 9, as we see over here. And then we add on 1 over x squared plus 9. So now everything is in an integrable form. So therefore, if we now attempt to integrate, we're integrating 1 plus x over x cubed plus 9x with respect to x. So this is the same as integrating 1 over 9 lots of 1 over x minus 1 over 18 lots of 1 over x squared plus 9 2x over x squared plus 9 plus 1 over x squared plus 9. So we're integrating this all with respect to x. So if we integrate each term, here we've got 1 over 9 times by the natural log of x. Here we've got minus 1 over 18 times by the natural log of x squared plus 9. And then here, recognizing that this is of the form 1 over x squared plus a squared, of course a squared is equal to 9, so therefore a is equal to 3. We have over here 1 over 3 times by the arctan of x over 3. And don't forget your plus c. So now if we tidy all of this up by taking out a 1 over 18 to combine these logs, we've got 1 over 18 times by 2 times by the natural log of x minus 1 over 18, rather minus the natural log of x squared plus 9 plus 1 over 3 times by the arctangent of x over 3 plus c. So if we power slide this up, we've got 1 over 18 times by the natural log of x squared minus the natural log of x squared plus 9 plus 1 over 3 times by the arctangent of x over 3 plus c. So if we combine these logs, we've got 1 over 18 multiplied by the natural log of x squared over x squared plus 9, and then we add on the 1 over 3 times by the arctangent of x over 3 plus c. That is our final answer. Okay, so let's just stop the video. That's our final answer. Example number 15. For part A, we have to express x to the 4 plus x over x to the 4 plus 5x squared plus 6 as partial fractions. Now, to do this, hopefully on the bottom straight away you can spot we've got a hidden quadratic. The bottom we can factorize as x squared plus 2 lots of x squared plus 3. And on the top we've still got the x to the 4 plus x. Now, if we were to express this as partial fractions, hopefully you can see we have an x to the 4 divided by an x to the 4. So essentially, what we're left with is a constant term. So all of this is equivalent to a, our constant term, and our remainder will be a cubic divided by a quartic. So we have a plus bx plus c over x squared plus 2 plus dx plus e over x squared plus 3. Now let's multiply everything by x squared plus 2 lots of x squared plus 3. So if we do that, we've got x to the 4 plus x. This is equivalent to a lots of x squared plus 2 lots of x squared plus 3 plus bx plus c lots of x squared plus 3 plus dx plus e lots of x squared plus 2. And now we need to compare coefficients. So let's just write this down. We will now compare coefficients. So if we compare the x to the 4s, we've got 1 on the left hand side, and on the right hand side we've got a times x squared times x squared, so the coefficient of x to the 4 is a. So in conclusion, a is equal to 1. If we compare the x cubes, you can see on the left hand side we've got 0 of them, but on the right hand side we've got bx times by x squared, that gives an x cubed. And then we've got dx times by x squared, that gives an x cubed. So we've got 0 equals b plus d. If we now compare the x squared terms, on the left hand side we've got 0 of them, and on the right hand side we've got here x squared times 3 plus 2 times by x squared, and then we're multiplying all that by a. So we've got in total 5a, and then we've got here c times by x squared, then we've got e times by x squared. Now we know that a is equal to 1, so we've got 0 equals 5 times by 1, which is 5, plus c plus e. So therefore, well, we'll leave this minus 5, we'll take the 5 to the other side, so we've got minus 5 equals c plus e. And now if we compare the x terms, on the left hand side we've got one of them, and on the right hand side, well, we've got bx times by 3, so we've got 3b, and then we've got dx times by 2, so we've got 2d. So let's now compare the number terms. If we compare the number terms, we've got 0 on the left hand side, and on the right hand side we've got 2 times by 3 times by a, so we've got 6a. And then we've also got c times by 3, and then we've got e times by 2. So knowing that a is equal to 1, we've got 0 equals 6 plus 3c plus 2e. So we've got minus 6 equals 3c plus 2e. So if I call this equation 1, this equation 2, this equation 3, and this equation 4, we can solve equation 1 and equation 3 simultaneously. So let's just write that down. From equation 1 and 3, you can see here b is equal to 1, d is equal to minus 1. And from equation 2 and equation 4, we've got c, which is equal to 4, and e, which is equal to minus 9. So knowing that, we can substitute all these values back into this right hand side here and conclude that x to the 4 plus x over x to the 4 plus 5x squared plus 6, this is equivalent to 1, plus x plus 4 over x squared plus 2 minus x plus 9 over x squared plus 3. Okay? Now, I know I'm going to integrate all of this. So I need to write this result and this result in an integrable form. So we've got 1 plus x over x squared plus 2 plus 4 over x squared plus 2. Then we've got minus x over x squared plus 3. And then we've got minus 9 over x squared plus 3. So now if we tidy this up even further, we've got 1. Now this over here, I want this to say 2x over x squared plus 2. We want it in the form f dash over f, but I don't have a 2x, instead I've got an x. So I need to multiply by 1/2. Okay? Now here, we're going to rewrite this as 4 lots of 1 over x squared plus 2. We can integrate something like this quite easily. And then this result, well, I want it to say 2x over x squared plus 3, but I don't have a 2x, I've got a 1x, so I need to multiply by 1/2. and then we've got minus 9 lots of 1 over x squared plus 3. So now for part B, when we come to find the integral of this result over here, you can hopefully see here then, this integral is equal to the integral of 1 plus 1/2 lots of 2x over x squared plus 2 plus 4 lots of 1 over x squared plus 2 minus 1/2 lots of 2x over x squared plus 3 minus 9 lots of 1 over x squared plus 3. So this is what we're integrating. So if we integrate all of this, integrating 1 we end up with x, integrating this result we end up with 1/2 times by the natural log of x squared plus 2. Integrating this result, well, you can see this is of the form 1 over x squared plus a squared. Of course, a here is root 2. So here we've got 4 lots of 1 over root 2 times by the arctan of x over root 2. Over here we've got minus 1/2 times by the natural log of x squared plus 3. And then we've got over here minus 9 lots of, well here, this is of the form 1 over x squared plus a squared. A is equal to root 3, so here we've got minus 9 lots of 1 over root 3 times by the arctan of x over root 3. And don't forget we've got a constant of integration. Now this term and this term we can combine. So we've got the x plus the 1/2 times by the natural log of, the mod of, x squared plus 2 over x squared plus 3. And then here we've got 4 times by 1 over root 2, that's 2 root 2. So we add on 2 root 2 times by the arctan of x over root 2. And then minus 9 times by 1 over root 3, that's minus 3 root 3. So we subtract off 3 root 3 times by the arctan of x over root 3. And then we add on the plus c as well. So this is our final answer in a simple form. Okay.